So in this demonstration, we're going to talk about relative and absolute age determination. So when we're talking about working out how old a rock is, we're either going to try and ask ourselves is which rock is older, that gives us a relative age, or we're going to say how old is it, that will be an absolute age. So let's begin with an example of relative ages. I'm sitting on a lovely white pegmatite, lots of lovely big crystals. But just over here, I've got some metamorphosed sedimentary rocks. I can see the metamorphic foliation really clearly. But if I follow that metamorphic foliation until I reach the pegmatite, it's cross-cut. A cross-cutting relationship tells us about relative age. The pegmatite must be younger than the metamorphosed sediments. Otherwise, it couldn't possibly cross-cut the original fabric in the metamorphic rock. So this tells us relative age, older and younger. But what now if I wanted to know how old this pegmatite actually is? I don't know that from this exercise, I just know that it's younger than the metamorphic rocks. What I would then want to do is analyse some of the minerals that it contains. And I'd be looking for minerals that contain radioactive elements, because these radioactive elements decay. And what I know is what's called the half-life for that decay. I know how long it takes for there to be half as many of those radioactive elements. We call the radioactive element the parent, and we call what it decays to the daughter. So what I'm going to do is I've got a bag of elements here. They're all the same radioactive elements. And I'm going to just pour them out onto this nice rock surface. Spread them out a bit. There were 64 of them. Now what I see is some of them are black and some of them are white. Let's just assume here now that the black ones are the parents and the white ones have already decayed. So this is after one half-life. So I'll take all the decayed ones away. Take me a few minutes. Now statistically, that should be half of them gone. Of course, in reality, it's not necessarily exactly half. But if I did it hundreds of times, it would average at a half. So now one half-life is gone. So let's say the half-life of the element was 700 million years. And I had this many of my parent elements remaining, and that's how many daughters I'd had. I'd now know that my rock was 700 million years old. Well, let's pick them all up now, and let's do another half-life. So we're going to wait another 700 million years, and we're going to let this guy decay. And in a half-life, shake them up a bit. There we go. So now I've lost some more of my, I've created some more daughters elements. There we go, take those away. And I should now have roughly a quarter of what I started with. So I now should have 1/4 are going to be my parent elements. 3/4 are the daughters. So I've had two half-lives. If the half-life was 700 million years, Now I'm at 1,400 million years, 1.4 billion years. Okay, so I'll pick them all up again. We'll wait another 700 million years and we'll allow all that lot to decay again. There we go. Take away the daughters. I've only got 1/8 of them left now. 7/8 in the bag. Another half-life over. Now I've got 3 half-lives, all at 700 million years. That's going to be 2,100 million years, or 2.1 billion years. We'll take one last half-life just for fun, but I think you're hopefully getting the hang of it now. And this will take us up to 2.8 billion years. Well, I'll only have a 16th left. Oh dear, one of them fell in the sea. Such things happen, and there we go. Of course, in the perfect world, that would be 4 remaining, and the 4th one is floating away. So using the half-life of radioactive elements, it's so long as we know that half-life, we can determine the absolute age of the rock by the ratio of the amount of parent elements to daughter elements in the rock. Thank you for listening.